Thank you very much. So I will recall what we did the last time. Essentially, I spent some time defining the arithmetic intersection product of two Hermitian line bundles on an arithmetic surface. And the goal was stating an arithmetic Riemann-Roch formula. So this will be involved a characteristic classes side of the formula. And after that, I was discussing a little bit about coherent cohomology on a Riemann surface. So I had a compact Riemann surface X, L line bundle on X. I recalled that the cohomology groups of this line bundle are canonically isomorphic to Dolbeault cohomology groups. And this Dolbeault cohomology is the cohomology of the complex, in this case reduced to two terms, and arising from the holomorphic structure of the line bundle. That means that it's an infinity line bundle together with a del bar operator. And I also said that we would choose metrics on the tangent bundle, metric on the line bundle, that from the tangent bundle we would get volume form, and that from all these elements, these infinite dimensional spaces come with a L2 Hermitian product. And so here and here. And so I observed that since H0 is the kernel, or is isomorphic to the kernel of del bar, and this lives in A00. So this cohomology space will inherit a L2 pairing from here, so H2 inherits L2 structure. And I wanted to explain that the same can be done for H1. In the case of H1, actually can canonically identify the H1 with the kernel of the adjoint of this operator with respect to the L2 pairings. So del bar star is the formal adjoint of del bar with respect to the L2 pairings. And this means it's characterized by the following relation given on L2 pairings of sections. So you take the del bar of a section in A00, and you couple it against 0 on section, and then as in finite dimensional linear algebra, you want this relation, and this defines an operator, and actually you can give local formulas which don't even require to be on a compact variety. Okay, so this is the content of Hodge theory, that you have this identification, and once you have this, so this, since this del bar operator goes the other way around, this kernel will be contained in A01. And then, again, through this isomorphism and the L2 pairing here, we have an induced L2 on H1. And these induced metrics are called L2 metrics on these cohomology spaces. So just another way of seeing this, that in the case of Riemann surfaces is maybe too exaggerated to use, but it's the right way of extending this kind of observations to higher dimensions, is that instead of seeing these spaces as kernels of del bar operator or del bar étoile star, these are also kernels of Laplacians. So actually, if you delta 0, 0 del bar, so as this operator, so you apply del bar from A0, 0 to A0, 1, and then you apply del bar star. So you get this endomorphism of A0, 0, which is, by definition, the Laplacian of 0, 0 forms or sections. And the same can be done for the space of 0, 1 sections. And then actually what you have is that the H0 is going to be the same thing as harmonic sections with respect to this operator, and the H1. So this is easy to see from the adjoiners of this operator. So these are harmonic sections. So hence we got cohomology represented in as harmonic L-valued forms. So this is how this picture generalizes to higher dimensions, and also shows that from the point of view of these operators, for coherent cohomology, we only need these 0 eigenspaces. So later we'll need more. So just to finish this this part, so I will use the following notation. So the determinant of the cohomology, so this bullet, this is a point of, so the determinant of the cohomology of L is going to be the maximal exterior power of the H0 10 the maximal exterior power of H1 dualized, or sometimes I also write -1. So this is a one-dimensional C-vector space, and these L2 structures, by taking exterior powers and duals and, well, tensor products and duals, induce an L2 metric here. So this also carries L2 metric. And the notation for this metric will be HL2. Okay. So we have used Hodge theory to define this L2 metric, and it looks like a good candidate for a metric on the cohomology, on the determinant of cohomology. But what happens in the arithmetic Riemann-Roch theorem is that this is actually not enough. So you need to take into account. So this is the content of the equivalent. The right, say, Hermitian metric on the determinant of the cohomology for the purpose of a Riemann-Roch statement. Is a slight modification, well, not a slight modification, it's a serious modification of the L2 metric that will take into account all the eigenvalues of these Laplacians. Is modification of this L2 metric that takes into account the whole spectrum on these operators. Actually, since we are in dimension 1, we will only need the positive eigenvalues of the Laplacian on 0, 1 sections, which is actually the same thing as the positive eigenvalues of the Laplacian on 0 section. So let me explain how this goes. So let lambda n, well, be the strictly positive eigenvalues of delta 0, 1. As I said, I could also use, because we are in dimension 1, delta 0, 0, also use, which, for instance, if your line bundle is trivial, delta 0, 0 is maybe easier to use because it's a Laplacian on function. So this is an easier object that the Laplacian on 0, 1 forms. And so we consider these strictly positive eigenvalues. And here I'm implicitly using that this is a discrete set. And of course that, yeah, this is a discrete set. I will say more in a second. And you form the following function. Zeta 0, 1 del bar is going to be the zeta function on all these eigenvalues. And of course, it's not here that this thing converges, but it turns out, thanks to growth estimates for the eigenvalues coming from the theory of elliptic differential operators, this series absolutely converges for real power of S bigger, strictly bigger than 1, and hence defines a holomorphic function in this region. So in this region. And what turns out is that actually it can be shown that it has a meromorphic continuation to the whole complex plane. And the important thing for us is that at s equal to 0, it's holomorphic. And the way how one proves these kind of things is parallel to the proof of the meromorphic continuation and functional equation for the Riemann zeta function. You introduce a theta function. So in the case of the Riemann theta function, you use the Mellin transform. You use this L function attached to a holomorphic theta series, and then you use that this is the modularity to prove the functional equation, as well, the usual stuff with L functions. So here, of course, this is not going to be the Mellin transform of holomorphic function on a line, but it's going to be the Mellin transform of some real analytic function. And the idea is try to mimic the proof for the Riemann zeta function applied to this real, like say, C infinity function, which is called the spectral theta function. So the way to prove this you introduce the spectral theta function, which is by definition the sum, and this can be also written as a trace of this thing that you can take as something formal, but it's actually a true operator, minus the dimension of the kernel of L01. And then what replaces the use of the functional equation of the holomorphic classical theta function is actually studying what happens when t goes to 0 and when t goes to infinity. So you have some asymptotics for theta t goes to infinity and t goes to 0. The asymptotics as t go to infinity correspond to both estimates for the eigenvalues. So this is kind of growth of lambda n as n goes to infinity. And for t equals 0, it's a bit more complicated. You need the theory. So this uses a bit more the theory of the hit operator. And somehow you need to obtain local expressions for this operator, really define it kind of by hand. And once you have reasonable estimates as t goes to infinity and t goes to 0, so you can see, or you can properly define this zeta function as a Mellin transform of this spectral function. So somehow the behavior as t goes to infinity in the case of the theta function, the holomorphic one, the typical one, corresponds to the behavior at infinity, of course, and then the behavior at t goes to 0 for the holomorphic case, you get it by the functional equation, the modularity, and then from the behavior at infinity. So it's essentially the same proof. Okay. Yeah. So once you have this expression, well, so you need these two things to give a meaning to this integral. And then the expansion as t goes to 0 is used to prove this meromorphic continuation and show that at s equals 0, it's holomorphic. Okay. So why do we want that it's holomorphic at s equals 0? Is because we need the following definition. We define the determinant of the 0-1 operator actually restricted to the space orthogonal to the harmonic, so to the kernel. Usually sometimes puts a prime. Anyway, so this is the exponential of minus derivative at s equals 0 of this function. Okay, and if you make a formal computation, this is the product of all the eigenvalues, which is, I mean, is infinity, right? But so this is, if you, for an exercise, you see what happens with the Riemann zeta function. This kind of procedure gives you that the factorial of infinity is something like a square root of 2 pi or something like that. So, okay. There are other ways to regularize these infinite products that one finds in the physics literature. Sometimes these different ways of doing this coincide, sometimes not. So this is the one used in the work of Jacquet. So this is a very particular case of, or the log of this, actually, remark, minus the derivative of 0 of this zeta function is a particular case of holomorphic analytic torsion. So later in a modified setting, these eigenvalues will be the eigenvalues of mass forms. Okay, so the definition of the Klein metric is now easy. So you rescale this L2 metric by this determinant of this Laplacian. Okay, so this is the Klein metric. And it depends on the choices of metrics, on the holomorphic tangent bundle, and on. Okay, so it really depends on this. Okay, so this is maybe the most important ingredient in the formula of Jacquet, at least the most exotic one. And I'm very close to the statement of the theorem. I just need to rigidify a little bit the situation and introduce integral structures. So the determinant of the cohomology will be seen as having a Z structure, and then from this and this metric, I will be able to pop up a number. So, well, let me erase. So, arithmetic variant. Now you suppose that you have arithmetic surface. And L bar is going to be our emission line bundle on X. And I will fix on the tangent bundle smooth our emission, the tangent bundle of the associated Riemann surface emission metric, because I need this for the equivalent metric. So fix. So in later talks, we will specialize to hyperbolic type metrics. And well, I can look, say, at the coherent cohomology of this line bundle. So these are going to be Z modules of finite type. Z. Well, the H0 is clearly torsion-free. So this one is torsion-free. So I can define the determinant before just taking the maximal exterior power. So this will be a rank 1 Z module. And I want to do the same thing with the H1. The H1 could have some torsion. So to define the determinant, you just use a two-term resolution by free Z modules for H1. So this is a very particular case of the Knudsen-Mumford construction of the determinant. So very particular case of Knudsen-Mumford. Determinant of cohomology. Well, of cohomology or determinant of a perfect complex. Of coherent sheaf. Finite complex. So what you do is you present your module by locally, by free Z modules of finite type. And then you define the determinant of the H1. That's by definition. So principle, there is a choice of resolution. So you take the determinant of M, which is now defined. So power -1. Tensor the determinant of, wait, did I put it the right way? No. So I guess this way. Okay, so of course there is a choice here, but and it's Z module 1, okay, so it is not a big deal. So this is Z module. But this kind of constructions you can do more generally if you replace H1 by a perfect complex. So this would be a locally free resolution of coherent sheaves. And this thing is unique somehow or well-defined up to unique isomorphism that comes from comparing two resolutions. This is something that we know how to do in homological algebra. And when you base change to the complex numbers, of course, you recover the determinant of H1 in a canonical way. Or maybe up to sign, but in any case, since we want to create real, we are going to take norms of sections of these objects to create numbers. Even if this is up to sign, it's okay. So then you define the determinant of the cohomology of L, curly L, as before, but for the H1 using this construction. So the Z modulo of rank 1. Well, yes, Z modulo of rank 1. So after base changing to the complex numbers, you have a Coulomb metric because of the choices of metrics they made. After base change to C, it comes with a Coulomb metric. And now from this structure of Z modulo of rank 1 and the Coulomb metric, we can define a number which is the arithmetic degree. So we already saw this several times. So then take Z basis of the determinant of the cohomology, call it E. It's unique up to sign. And then define. So these are actually a very particular example of arithmetic degree. So the arithmetic degree of this determinant of cohomology with this Coulomb metric that I put in index. So this is just minus log of the Coulomb norm of this element, which is well defined. So this is a real number. Okay, so this settles the cohomological part of the arithmetic Riemann-Roch theorem. And I would like now to state the theorem. So just a small remark. Of something I have not done already. So in the left-hand side of the Riemann-Roch theorem, there was this Euler class. Sorry. There is in dimension 2. I didn't define anything like this so far, and I won't do it precisely. So there are some comments in the notes. I just will explain what is the analog for semi-stable arithmetic surfaces. But the analog of the Euler class will be an invariant that measures the band reduction of the arithmetic surface mod P. Okay. So the statement, this is the statement the theorem of Jacquet. So again, the thing is that of an arithmetic surface. We fix our mission line bundle L. And we fix a metric on the holomorphic tangent bundle on the associated Riemann surface. And by duality, this metric on the tangent bundle induces a metric on the cotangent bundle. And I will use this metric as a metric on the dualizing sheaf of this arithmetic surface. So by duality, we have in particular a metric on the cotangent, which is the dual of the tangent. And we'll use this and use this to metrize the relative dualizing sheaf of this arithmetic surface. Well, just to be sure that all the ingredients in the statement will be defined, so I will just recall how the relative dualizing sheaf can be constructed in this case. So we have an arithmetic surface, which is a proper scheme. Well, with there were all these views of hypothesis of a spec Z, a crude dimension 2. It's automatically projective, and it's regular by assumption, and so we can put it in a projective space, some dimension n, through a regular inversion. So the condition of being a regular inversion says that there is a normal vector bundle. So if you take the ideal defining the x inside Pn, of x in Pn, then the quotient I square is locally free. Of some rank R that is considered dimension of this immersion, and then the normal bundle to this information is just the dual of this thing. So definition of the dualizing sheaf uses the determinant of this bundle and also uses the determinant of the relative tangent bundle here. This is smooth morphism, so this has a tangent bundle. So TP relative tangent bundle. And then actually the way of obtaining the relative dualizing sheaf is actually in this case it's really the determinant of the coherent sheaf of Kähler differentials. And this determinant, as before, is obtained by a locally free resolution. So here, and then here you have the dual of this. You have a resolution like this, and then that the determinant of this object here has to be the determinant of the sheaf of Kähler differentials. Actually, by definition, tensor, the determinant normal bundle. So, sorry? Yeah, the normal bundle is, yes. I only put the parentheses. Yes. So, okay, so you see that this is then the determinant of the cotangent. Well, and then this is a relative tangent. It has a cotangent. And then tensor the determinant of the normal bundle. So this is the relative dualizing sheaf. And no, X is regular, and this is used in this here. Yeah, exactly. So, but you still have this exact sequence. And I use this exact sequence to define the determinant of this object as the determinant of this object tensor the dual of the determinant of this. So these are defined. So this is the way of defining. And so this is the dualizing sheaf, is the line bundle. And so as I said, these constructions of determinants of perfect complexes are, well, maybe I just said in a very particular case, but are compatible with base change. So when you base change these to the complex numbers, you recover the cotangent space of the Riemann surface. So over after base changing to C, you recover this thing, or maybe I should put an index here. And this has a metric. So this gives, so this way we obtain tries line bundle, which is the relative dualizing sheaf, with this choice of metric that, as always, I will denote with a bar. So this metric, which is not explicit in the definition, is the one coming from the tangent bundle that I choose. And I think that now we have all the ingredients to state the theorem of Jacquet. For arithmetic surfaces, of course, and the theorem goes as follows. So with the previous, in the previous setting, equality of real numbers as follows. So on the one side, we have the arithmetic degree of the determinant of cohomology, and on the other side, we'll have a combination of arithmetic intersection numbers corrected by some topological term. So, sometimes I just forget the determinant. Let me put it. So you have the that hat of the determinant of cohomology. This comes with a 12. If you look at the Hirzebruch Riemann-Roch statement, this is the 12 in the denominator of the tot genus. So if you want, this is a 12 of the denominator of the tot genus in degree 2. So there will be this term that I usually write delta. This is to be the analog of the C2 in this case with a hat. So, but I didn't really define this. It can be defined, and it's just a number. So there will be the arithmetic self-intersection of the canonical sheaf plus 6 times L bar intersection with L bar tensor the dual of the canonical. And then there is this corrective term, which is, so this is the genus of a connected component of the Riemann surface of complex points. Then we have the number of connected components. And then again, this log derivative of the Riemann zeta function. And delta is an expression that suggests it's a finite intersection number, measures bad reduction. So this is to be a finite sum. And if actually there is a general way of computing these coefficients that cohomological way, which is through arctic conductors. In the particular case, if X has semi-stable reduction everywhere, so I essentially mean, at least if you go to the geometric fibers in characteristic P, you have they have normal crossings like this. Then you just count the number of singular points in the geometric fibers. No. Mm-hmm. No. And he counts the number of singular points in, say, XFP bar. And actually, it can be defined as a characteristic class in the context of Arakelov geometry. C2 hat, so this is just a Corinne sheaf, and we are used to work with Hermitian vector bundles. So you use a resolution as before. You introduce some auxiliary metrics. You define a C2 hat by using the expected compatibilities of C2 hat with exact sequences, and then you have to make a correction to compensate the auxiliary choices of metrics. And then you get something that doesn't depend on anything and can be computed this way. Okay, so this number here, we saw it in the talk of Qingyi Yuan, for instance. The reason why it appears here is still a bit mysterious, and it's not clear that there is any relation between both things. I never managed to understand this. So it appears. And it was quite a surprise at their time that they would see this appearing there. OK, so we'll see an application of this theorem in the context of curves later, so by the end of the school. And I will also need a variant of this theorem that applies to modular curves. And as we saw in previous lectures, in modular curves, there are complications due to the structure at infinity, due to this compactification that causes that the natural invariant metrics coming from the group presentation of the symmetric space, these metrics will have some kind of singularities. And in all the discussions I did, it will be possible to define these arithmetic intersection numbers by using the formalism that was already mentioned several times, so Bost and Kuhn and Burgos-Kramer-Kuhn. And there will be a right-hand side or a possible right-hand side. And the problem will be at the level of the left-hand side, because as we will see, if we work with the invariant metric on a modular surface, the Laplacian here, I use 0, 1 Laplacians, but as I said, we can work with Laplacians on functions. And in this case, this will be essentially the classical hyperbolic Laplacian, and we know it has continuous spectrum. So parameterized by Eigensen series. So already the definition of the equivalent metric makes no sense. And even if you have a definition for equivalent metric, still you need to prove a theorem in these lines. which is another story. So I will present what can be done in this setting based on the work of Anna and me. Anna will give some complimentary lecture this afternoon, I think. So the idea to keep in mind will be the setting of modular curves, but I will make a general discussion. So I will call this section or this paragraph an arithmetic Riemann-Roch formula modular curve. It will apply, as I say, much more generally than for modular curve, but I think that if I call it this way, it's pretty clear what kind of phenomenon I have in mind, so the gas mainly. So let me just put in words what I just tried to explain. So now imagine that you have an arithmetic surface. Well, I'm not going to give a proof of the theorem of Shimura. It's extremely technical and very long. Yeah. So even if you want to prove it for arithmetic surfaces, the method makes that you need to prove it in any dimensions. So it's yeah, it could take time. So we have now an arithmetic surface. Imagine a arithmetic model of a compactified modular curve. So that its complex points will afford a kind of parametrization by the upper half plane mod out some groups together with some cusps, such that the set of complex points is a union, a finite one, of course, of Riemann surfaces of this kind together with cusps. So its component is supposed to be compact. So this is supposed to be compact. And the gamma i's are going to be, so just think of congruence groups, like SL to Z or gamma dot n that we'll review later, the one you prefer. So these are all particular cases of function groups. So where gamma I usually consider my groups in PSL2 of R because this is what the theory of function groups does. And so it's a function group of the first kind. So this means that gamma I is discrete. And then the first kind condition is exactly this, that when you consider this quotient, then you obtain an algebraic curve, an open affine curve maybe, and that you can compactify it by adding some cusps. So this is the first kind condition. So examples that we all know, so PSL2 of Z, or groups like gamma n for n big, or also gamma not n. This if you take the image in PSL2 of R, etc. Okay, so this is the setting, and in the once you have this presentation in the arithmetic Riemann-Roch theorem, it's very tempting to use as metric on the tangent bundle precisely the metric coming from the upper half plane, which is invariant under PSL2 of R. So very tempting. On the tangent bundle, and hence also the dualizing sheaf, use it's not the an invariant metric, but okay, the invariant metric coming from the upper half plane. So it's just unique up to constant, and it's actually this expression that we already saw in coordinates in the upper half plane of this form. So tau is the coordinate on H. So because this is invariant under the action of PSL2 of R, so somehow this descends to the quotient. But of course, as it is defined, it only descends to this quotient. It doesn't descend to the cusp. So this causes some problem. So descends to a metric on XC minus cusps. So cusp is the union of all these cusps. And so it has two problems. So the one that we just said is that and we saw in previous lectures, it doesn't extend to a smooth metric on the cusp. Does not. So what does it mean that it doesn't extend to the cusp? Well, to talk about extension about the cusp. So this is a metric only defined in the tangent space of an open Riemann surface. So I need to extend the vector bundle, and I need to extend the metric. So don't extend. Let me. The case is that whatever extension I choose, the metric of the vector bundle, or the line bundle in this case, the metric is not going to extend to a smooth metric. So, and then as we saw the other day, there is a particular best choice of in the lecture of Jose, there is a best choice of the extension of the tangent bundle that will make that this metric is actually log singular. But there is an extension which is unique of, let me call this U, so that I can make the difference of TU as a line bundle on XC that makes this metric log singular. So, and this extension is precisely, it's not the tangent bundle of the compact Riemann surface. It makes the metric log singular, at least in the neighborhood of the cusp. Log singular or log singular, I don't remember. Singular at cusp, okay? But there is another problem that I just hid, is that these groups can have torsion, like PSL2R. And in the talk of Chini, we already saw that distortion can play also a role in the definitions of dual Lie shift. You have to take into account the order of the stabilizers of fixed point. So also singular at fixed points with non-trivial stabilizer, of course, of gamma I. So these are kind of orbifold singularities. This also will enter with the suitable modification of the tangent bundle, will also enter in the theory of log singular metrics. Yeah, they are more gentle than the cusp ones, but they also pose problems. So we'll also, after suitable modification of the U, this will also enter into the log singular setting. But I mean, the singularities are less worse than the true log singular ones. So already for the trivial bundle, trivial Hermitian line bundle on the arithmetic surface, and with this choice metric on the tangent bundle, I would like to have a Riemann-Roch statement because this it seems interesting. It is the first case to try to extend to try to extend the result of Gilles-Soulet to the theory of Burgos, Kama, and Kuhn. And it also looks maybe arithmetically interesting, at least for modular curves. So I would like an extension of arithmetic Riemann-Roch of Gilles-Soulet to include this type of singularities on the tangent bundle. So, and then for the Hermitian line bundle, so this is only the part of the tangent bundle. There is also the Hermitian line bundle in the theorem of Gilles-Soulet. For this, I don't have any general feeling of what is the right hypothesis. So actually, I will, in this talk, I will just treat the case of the trivial Hermitian line bundle. So actually, we consider only as L bar the trivial line bundle. So I will give a formula in the lines of the arithmetic Riemann-Roch in this setting. And this is essentially the best we can do so far. So if you don't have torsion, you can allow powers of the canonical shift, but otherwise, this is all we can do, unfortunately. OK, so let me refine a little bit the setting. I will now be a bit more precise about the arithmetic surface. I will suppose that I have an arithmetic surface that is defined for the ring of integers of a number field. So by this I mean that the geometric fibers are so K is a number field, and so this is arithmetic surface. I will suppose then that the complex points are indexed by the embeddings. And for each embedding, I will have a function group together with cusps. And I will require that the cusps and the fixed points of these groups come from sections of this. So also assume that we have sections sigma 1, sigma n, say, from a spec OK to X, generically disjoint. That gives the cusps and elliptic fixed points corresponding to cusps and fixed points. And more precisely, I may suppose to say that sigma 1 to sigma k for some k correspond to the cusp, and the rest correspond to the elliptic fixed points. And we'll also introduce notation for the orders of the stabilizers. So say sigma 1, sigma k give cusps, are the cusps. And sigma k plus 1, sigma n, the fixed points. And I will introduce the orders of stabilizers that I will call ek plus 1 en bigger than 2 orders of the stabilizers. And it will be convenient to declare here that the orders of the cusps are infinity. OK, then the invariant metric that I mentioned is log singular as a metric on the following twisted version of the dualizing sheaf. So as in the talk of Qingyi-Yuan, I will take into account the stabilizers of the elliptic fixed points or the cusps. So this will be 0 for the cusps. So I consider this. So I see the sigma I as defining a divisor in X. And so this is actually a Q line bundle. So it means that what is really defined as a line bundle is a power of this. So, so I will consider this as a Q line bundle. But since the arithmetic intersection numbers are bilinear with respect to tensor product, I can actually extend the arithmetic intersection pairings to Q line bundles, Q Hermitian line bundles. So let me state the theorem where there will be a series of undefined objects that I will try to explain today. So there exists let me say it like this way. It will be a bit vague. Spectrally define fluid metric on the determinant cohomology and an equality. Okay, and also kind of canonical metrics. So the fact that in the Riemann-Roch statement, instead of now being able to consider the intersection, self-intersection of omega, so now we'll only be able to consider this the self-intersection of this object, means that we have to correct the Riemann-Roch formula by taking into account some contributions of the boundary. So in canonical metrics, the pullbacks of the canonical dualizings that we introduce later, such that there is an equality in R, 12 times the arithmetic degree of the trivial sheaf with a equivalent metric minus this delta. And then I will have a contribution coming from these things with their metrics that will be weighted by this. So there is a square here, the arithmetic degree. So the metrics of this, on these line bundles, I will write W. So this was for equivalent, this was for Wolper. So Wolper is a specialist of Teichmüller theory. And this should be equal to the self-intersection of this Q-line bundle with this choice of hyperbolic type metric. And then you will have some contribution, actually. From sections, different sections that can intersect at finite places. And then depending on the day, I put a constant, which is similar to the one in the theorem of Gilles-Soudet, or I absorb the constant in the equivalent metric. So, but yeah, so this depends on the normalizations, but it's important to know somehow it exists. I won't say anything about this constant. But so I need to explain you where these terms come from. This is already covered, but the theory of Burgos-Kuhn that was and Bose-Kuhn that was a little bit explained. And I also have to explain how this goes. So I will just say some word about this term here. If you are in situations like PSL2 of Z, which Anna will review this afternoon, the problematic points are the cusp and the elliptic fixed points, so the typical, the square root of -1 and the third root of unity. So this, well, if you the modular, the course modular curve seen as P1 of Z, everybody's here is defined over Z actually, and for the cusp, this contribution will be 0, no problem, and for the elliptic fixed points, this contribution will be essentially the Faltings height of the corresponding CM elliptic curves. So these numbers sometimes can be evaluated in terms of L functions by the Choloselver formula, but in general they are, I would say, quite random quantities. So you can use them on moduli spaces of curves to define heights with at least in genus 0. So heights that will satisfy the usual finiteness properties. So this means that these numbers are very difficult to control. So you don't have general bounds or whatever. So this is truly a random quantity. So in only in arithmetic situations, they have a meaning like Faltings heights or whatever. So in any case, in this kind of statements for modular curve, this will be an extra source of L values. Okay. So let me explain this, the Wolper metric. So to define a metric, I allow myself working on a Riemann surface because it is a transcendental problem. So I will go back to a Riemann surface, X, and I will work on a connected one. So we'll have this shape. So there will be some cusp, and gamma may have torsion. So as exactly as for modular curves, the neighborhoods of the cusp can be parameterized by the typical Q coordinate in the Q expansions of modular forms. So a neighborhood of the, let P be a cusp. Then there exists Q, a holomorphic coordinate at P, which assigns to P the value 0, and such that the hyperbolic metric that before in the coordinate of the upper half plane I wrote this way looks like dq to the square q squared q to log q to the square. So square. Now I'm just not sure that there are so many squares. I don't know. So we saw this yesterday in the lecture by Jose. In the case of modular curves, this is a general fact in the function groups at least. Okay, so this depends on the notion of parabolic subgroup. That parabolic subgroups are to groups of translations, etc., etc. And then in the end, it allows you to show the existence of such a coordinate. And Q. So well, I said it exists, but I didn't say it's unique. Q is unique with this property up to a constant of modulus 1. So this means that if I declare that the norm of the Q at Q equals 0 is equal to 1, this, even if Q is not unique, this defines a metric on the cotangent space at Q equals 0. So this defines a Hermitian metric on the cotangent space of X at the origin that, of course, I identified with the cotangent space of a disk at the origin, right? So this is what D0Q means. So this is the Wolper metric in this case. This is the one that Wolper introduced. So this is a kind of regularization of the hyperbolic metric at a point. So at this point, everything bows up. So I declare, since I have a canonical coordinate, that the norm of this canonical differential up to something of modulus 1 is 1. So it looks quite algebraic. And the reason why for modular curves, the contribution of this term for a cusp actually will be 0, because the Q expansion principle is saying you that, well, first of all, that this operation here, taking the restriction of the cotangent bundle, corresponds to taking the 0th Fourier coefficient of a modular form. And then through this identification, this line bundle together with this metric, it just corresponds to the trivial Hermitian line bundle. So it has trivial arithmetic degree. This will be seen later, I guess. And you can do the same thing for fixed points. So let Q in X be an elliptic fixed point with a stabilizer of order K. Then you can do exactly the same thing. So the same way that the the stabilizers of cusps are parabolic subgroups, and these are conjugate in PSL to over R to the translation to tau plus 1. The stabilizer of an elliptic fixed point is also conjugated to a group of notations about the square root of -1. So, and actually, there exists, same thing. Canonical up to a constant of absolute value 1, a coordinate W such that the hyperbolic metric in a neighborhood of Q, which will center, no, not this one, will be the center of this coordinate, is of the following type. There, by the way, there are some typos in the notes. In particular, the metric I wrote for the fixed points is have the right constants. This is the right one. So here there is this K square, and then you have a W. Yeah, now I forgot. See. 2 minus 2 over K. 1 minus W2 over K to the square, where K is the order of the stabilizer. So if you want, is the, yeah, let me call it the torsion of the order. And this is in very, this easy to justify. So we didn't see anything like this yesterday, but it's also believable if you know that you remember the hyperbolic disk usually comes with this hyperbolic metric. I could put 1. The hyperbolic disk is the disk with this hyperbolic metric, and then you may make well the group of K roots of units by multiplication, and then you have you may take the quotient by this action. And this is the usual thing that you define you use in any course of Riemann surfaces or modular curves to put the complex structure on a modular curve. So you just say that this is isomorphic to D01. And the map from here to here just sends the coordinate z to z to the k. Of course, if there has a small problem at z equals 0, there is ramification, and if you push forward this metric, so you call this W, so through this map, so you push forward this metric, you get the metric I described. So so it's quite believable at least that there is a coordinate where this is possible. And then you do the same business. Then declare that the norm of W at the point W equals 0 is equal to 1. And this defines a metric on the cotangent space at this point Q. And this I call proper metric. So in the case, again, of elliptic fixed points on a modular curve, you can compare these. So if they correspond to elliptic curves with complex multiplications, you can compare this construction to the omega shift that we saw in Fabricio's talk, together with the Falting's L2 norm. So by using the modular interpretation. So and then before, as I said, in Q corresponded, in the case of a cusp, to Fourier, the classical Q expansions in the neighborhood of the cusp. Actually, this corresponds to functions in the neighborhood of an elliptic fixed point. So Fourier expansions. OK, now I will discuss a little bit the equivalent metric. I will be very brief, because I would like at least to explain this today, and then I'm lucky that Anna will give compliments. So I will just give brief things. So we look. So we want. OK. We have these cohomology spaces. So I have to put L2 metric here. So this is for the L2 metric. So this is pretty easy. So this is C for a compact Riemann surface. And the only thing I need is that the volume of this with respect to hyperbolic measure is fine. So this has a well-defined metric by declaring that the norm of 1 is the integral of the volume form on X. So this is the volume of X. And again, I don't want right now to make precise of the volume form, because I mean, yesterday we saw normalization using a factor 4 pi. The other day we saw a factor 2 pi. The normalization, if you want Ricci curvature -1, is a factor 2. And other people consider that you don't need any factor at all. So it depends on your taste. This space is dual to the H0 of the cotangent, if you want. And in here, the metric is canonical. So in this space of differential forms, we use a metric like the one Fabricio's talk. We use this. And why I put the 2 pi here, this has to do with the normalizations of Gilles-Soulet, which their L2 metrics carry this factor. So this defines something that is completely independent of the hyperbolic metric. And this is one of the advantages of working with a trivial sheaf. And this will give a well-defined metric L2 metric on the determinant of the cohomology of this. So it's not here. The problem, as I said, is in the analog of the equivalent metrics. So we know some. Yeah.
So you suppose gamma is a subgroup of gas2, so I assume gamma is a subgroup of the isometric group of H2, right?
Yeah.
But after a while, you also deal with some condition metrics. So somehow you assume it as subgroup of the holomorphic group as D, something like that. So is there any difference between them?
I'm not sure I'm understanding.
I mean, gamma is a subgroup of PS2R, so you assume somehow you assume gamma is a subgroup of asymmetric group of H2.
Yeah, but these are holomorphic because these are the Möbius transformations.
Because when you go further, after a while you do something Commission metric or some holomorphic stuff, so somehow I assume gamma become a subgroup of the holomorphic automorphic group, and D, when D is isomorphic to H2 something.
Yeah, but
regard D as a complex one-dimensional hyperbolic space. I suppose there is some difference by index 2, something like that.
by this, no, okay. So here the group is only involved through its action on the upper half plane. Do we agree? And which action is this? If you have A, B, C, D, then you act by sending tau to A tau plus B, C tau plus D. I mean, if you get a Riemann surface, I need kind of.
But you just take some group of PS2R, I suppose somehow you know the orientation, so somehow there's some element without orientation.
Yeah, but I don't get the point. So what I should do that?
There's no orientation issue here. I don't think so. Okay, we can tolerate it.
Yeah. Okay. So let me just say some word about the Quillen metric. So if you normalize the hyperbolic metric, like this, then you have a scalar Laplacian on functions, which is the same thing as A00 of H mod gamma. And for me, this means the functions on the upper half plane invariant under the action of the group, which is a typical hyperbolic Laplacian minus square minus x squared. Okay, so I said the scalar Laplacian because in Arakelov geometry we use the double Laplacians. So the difference between both is just a constant. So the del bar Laplacian, again depending on how you normalize your Cavet metric, will be just on 0,0 functions, just a multiple of this Laplacian. So to discuss the problems in the definition in the Quillen metric, I'll just discuss the spectral theory of this because this is the classical normalization. So before we use the discrete spectrum, here the spectrum before use discrete spectrum. Now, the spectrum of this operator on functions classifies into 3 parts. Spectrum classifies into discrete cuspidal. So this arises from this differential equation, where lambda is in this case, a strictly positive real number, and phi is C infinity, and actually L2 with respect to the hyperbolic metric. And actually, you have to impose a cuspidality condition, which is a vanishing Fourier condition. It has 4 modular forms, plus vanishing Fourier coefficient at cusp. I don't need any condition at elliptic fixed points. This is actually comes from the fact that these are orbifold singularities. And, okay, then you have a continuous spectrum So it goes as follows. So for every cusp, for every P cusp, you have a stabilizer of the cusp, which is a parabolic subgroup of R group gamma. And so this is conjugated to tau goes to tau plus 1, as before. And you find an Eisenstein series by the usual average formula, like this. These are not L2 functions. For any S, so this is valid for real power of S bigger than 1. So you have to take into account these things. Typically in physics, the way you would consider this equation is, okay, I take these solutions and I just want them to be bounded. Precisely, this is not the case of these things. I mean, or I want them to be integrable, and you restrict to this set of things. So this is not the case of Eisenstein series. This is the usual thing that you do naively in physics. And if you want to do quantum mechanics, then you have to take into account this. This is the continuous spectrum. Okay, so they satisfied that the Laplacian applied to the Eisenstein series is equal to this. They have a meromorphic continuation in S. In S, and with residues only in the real interval open 1, close, open 1 half, close 1. They are, hence in particular, no poles at the real, well, so at the line S equal 1/2 plus IR, so real power of S equal 1/2. This will be very important. So yeah, and so this is the line in quantum mechanics where you have where you have incoming waves and outcoming waves. So this is the separating line, and somehow, and then what else I wanted to say? Functional equation. So you define a vector of Eisenstein series by putting all the Eisenstein series in a vector. And then for this vector of Eisenstein series, there is a functional equation relating the value at 1 minus S with the value at S. And the relation between both vectors is given by a function, a matrix, Phi-S matrix of meromorphic functions. It's a matrix of whose poles again are contained here. Actually, they contain the poles of Eisenstein series. Whose poles somehow give or control the poles of Eisenstein series. Particularly, it's a nice function on the line 1/2 plus IR, and this is called the scattering matrix. And again, the scattering name comes from quantum mechanics. So okay, I will use, so I didn't finish the description of the Coulomb metric. So I'm taking a spectral presentation. Anna, I think, will use an equivalent one. So, but I still didn't define the Coulomb metric, so maybe this afternoon we'll have an approach for that. So next time I will finish the description of the spectrum. So I said that there are, no, three parts. So there is discrete, there is the continuous, and then there will be another one, which is the residual one, that arises from residues of Einstein series. So these both will give the discrete spectrum. This is the continuous spectrum, and we'll put them all in a kind of a spectral zeta function, analog to the one for the definition of the Coulomb metric. And this will be the way of dealing with the continuous spectrum and also the residual one. Okay, I stop here.